Good morning, good afternoon from the International Society, ISQGD. It is my pleasure to introduce our first speaker, Henry Adams from the University of Florida. The title of his talk is Vietoris-Rips Complexes of Manifolds.
Thank you so much, Mrinal and Azur, and thanks to ISQGD. So I'm at the University of Florida, but actually right now I'm back at my parents' place in Sacramento, California. So that's one of the beauty of online organizations. Um, First, let me mention AATRN, the Applied Algebraic Topology Research Network. So this is a an organization I've been involved with for a decade now. So we started after a thematic year at one of the math institutes, so the IMA in Minnesota. And so even prior to the pandemic, we had an online seminar. So now we have a very active online seminar. I think we have about 700 videos posted online. And on YouTube, we get about 16 hours watched per day. And we have 9,000 YouTube subscribers. And so this is a network that represents my broad research area, applied algebraic topology. Okay, so let me go into the topic today. I want to talk about Vietoris-Rips simplicial complexes. Um, so the definition is relatively short. You have two inputs. You have X, a metric space. Typically, you think a finite metric space or a discrete metric space. But today we'll also talk about the case where X is an arbitrary metric space, maybe a Riemannian manifold. And you also have a notion of size or a scale, R, a non-negative real number. And then from this metric space and the scale, you build a simplicial complex. Its vertex set is every single point in the metric space. And then its simplices are all finite sets of diameter at most r. So the diameter of a simplex is just the length of the longest edge. So first you add in all your edges, all points within distance r, and then whenever you have three edges forming a triangle, you fill in the triangle. Whenever you have six edges forming a tetrahedron, you form in the tetrahedron, etc. So here's a particular example where I have a metric space of approximately 20 points in the plane, and then the Rips complex at scale 0 is just the set of points. And then here I have the Rips complex at scale maybe 1 inch, and I connect all pairs of points within distance 1 inch. And then you see every time I have three edges forming a triangle, the triangle gets filled in. And then even if these points are in the plane and they're equipped with the planar Euclidean metric, you can get higher dimensional simplices. So here I have all of the edges of a tetrahedron. So I have this three-dimensional tetrahedron that fills in. Okay, and then certainly as the scale gets large enough, if the diameter of the metric space is finite, once the scale is the diameter, then everything fills in and you get a contractible simplicial complex at that scale. But at intermediate scales, you might be measuring small holes or larger holes that persist for different ranges of scales. Questions about the definition? Okay. So a little history. Vietoris invented these. This was around the time when we were developing different notions of homology and cohomology, and we had simplicial homology, but Vietoris wanted to define or define homology or cohomology for metric spaces, for broader classes of spaces. So he sort of took a limit as the scale was going to 0. Then he built, this family of simplicial complexes. And then since he could define homology for these simplicial complexes in the limit, he defined Vietoris homology and cohomology for metric spaces. Rips used these later in geometric group theory. So Rips proved that a delta hyperbolic group equipped with the word metric when you build this complex on top of it, it's contractible for all scales R that are at least 4 times delta. So this can be used to prove that you have finite dimensional Eilenberg-MacLane spaces for hyperbolic groups. More recently, Vietoris-Rips complexes have come up in my area, applied topology. They are a natural way to thicken a data set to approximate its shape. So maybe you sample 20 points from a data set. You wonder what shape was I sampling from? And so you increase the scale from small to large, and you maybe track which features persist for a range of scales. And that might be evidence that, oh, since my Vietoris-Rips complex was the shape of a circle for a range of scales, maybe my hypothesis is that my data set was noisily sampled from a circle. And there are now, there's now lots of theory about this pipeline. So if two metric spaces are close in the Gromov-Hausdorff distance, then the persistent homology of the output is close. And I've written one of my data sets, I've written one of my metric spaces as X and one of my metric spaces as M. This is because for this talk, I'm going to think M as a Riemannian manifold, and I'm going to think of X as a data set sampled from it or sampled nearby it. And so what this is saying is that in the limit, if you sample more and more data points, then your data set is converging to the manifold itself. So the persistent homology of your data is really converging to the persistent homology of the Rips complexes built on top of the entire manifold. And that's motivating our main question. For M, a Riemannian manifold, what can we say about this limiting object, the Rips complex of the entire manifold? So there's good software designed to compute persistent homology of Rips complexes. Data scientists are computing these things. And then I think it's the job of the mathematicians to figure out what is the limiting object? What are we actually approximating in the limit as our data sets get closer and closer to the nicest possible data set, which is sampling from a Riemannian manifold. Okay, so I haven't described these symbols, persistent homology, but let me talk about those a little bit more. So this part in orange is new, and I just want to give you some pictures of what I mean by persistent homology. Um, so here I have a two-hole torus in black, and then in blue I have points sampled from it. And so blue I would have my X, and then in black I would have my manifold M. And what this stability theorem here is saying is, for example, if I sample more and more points in X, and so if my data set X is converging to the entire manifold in the limit in the Gromov-Hausdorff distance, then the persistent homology of one is converging to the other. So here on these plots, I've drawn the persistent homology of this sample X. So the this is the persistent homology of the Rips complexes. Okay, so we have zero-dimensional persistent homology here. We have one-dimensional persistent homology here, and we have two-dimensional persistent homology here. So zero-dimensional persistent homology, you're going to have one short bar for each data point. But then as I build the Rips complex, all of the data points connect up, and eventually I have a single connected component measured by this bar. Now, for the one-dimensional homology, as I build the Rips complex, I might get these small noisy holes here. But as I increase the scale, eventually I recover the homology of the two-hole torus, which is 4 generators. 1, 2, 3, 4. Okay, so eventually I'll get these. You'll often see this noise pattern that as the short zero-dimensional holes fill in, that's when the short one-dimensional holes start. That's because if edges are forming, they're connecting components while they also might be creating loops. And as the short, one-dimensional holes are filling in, you'll get some short two-dimensional noisy holes. That's because as triangles are forming to fill in one-dimensional holes, some triangles will also create two-dimensional holes. Okay, but then you also have this range of scales where you recover the fundamental class, essentially the two-dimensional homology generator of this surface. So this is the persistent homology of X, the sample. And the stability theorem is saying that it's close to the persistent homology of the entire manifold if I built this Rips complex on an uncountable number of points, the entire manifold. I can't resist mentioning this beautiful data set that's not quite sampled from a manifold, but it's sampled from a stratified space. So cyclooctane is this molecule that has 8 carbons arranged in a ring, and then each carbon has 2 hydrogens sticking off of it. Okay, and this molecule can move around and stretch in different ways. But let's mod out by rigid symmetries. Okay, you can do a degree of freedom count and figure out that this molecule has 2 degrees of freedom. But what space is it sampled from? Okay, so these scientists, Martin, Thomson, Koutsias, and Watson, they built this beautiful data set where they sampled 1 million points from this configuration space, and then they actually triangulated the space from which they were sampling to figure out what it was up to homeomorphism. And this molecule, it lives along what looks like a sphere with an hourglass glued inside, but it's actually a sphere with a Klein bottle glued inside. So this molecule, its configuration space is this interesting algebraic variety or stratified space that's not quite a manifold. It's a sphere with a Klein bottle attached along 2 circles of singularity. Um, so um, for mathematicians, locally our Earth looks flat, but it's important to know that we live on a two-dimensional sphere, right? And similarly, as this molecule's moving around, it's important to know that locally there's 2 degrees of freedom, but as it moves from a higher energy configuration to a lower energy configuration, the map on which it's moving is actually this complicated space, a sphere with a Klein bottle. Questions? Okay, so that was all sort of motivation and why I'm interested in this question. What are Rips complexes of manifolds? So let me spend the next 10 minutes or so just telling you some things we know and all the things we don't know. We know a lot less than we do know. Hausmann proved a long time ago that if you have a compact Riemannian manifold, well, at small scales, you recover the homotopy type of the manifold. Um, but the idea of persistence homology is to vary the scale from small to large. So what happens later? All right. So in 2017, Michael Adamaszek and I worked out the case of the circle. So what happens when you build the Rips complex on top of the entire circle? We'll let Sn be the n-sphere with the geodesic metric and diameter pi. So when you're building a Rips complex on the circle, you immediately have an uncountable number of vertices. And once the scale R is positive, you immediately have simplices of arbitrarily high dimension, right? Because let's say my scale's, 2 inches. Well, if I just put 1 million points within 2 inches of each other, then I have a simplex of dimension 1 million minus 1 supported on all of those points. Okay. So when you build this Rips complex on the circle, you immediately get simplices of arbitrarily high dimension. Hausmann's theorem says you maintain the homotopy type of the circle for small scales. Okay, so so I'm increasing the scale from 0 to larger, and for small scales, I maintain the homotopy type of the circle. Once the scale is larger than pi, then I have all possible edges, right? At scale pi, I have this edge. And so once you attain scale pi, then the simplicial complex is contractible. And what is quite interesting to us is that in these intermediate scales, the homotopy type is all possible odd spheres. So you jump from the circle to the 3-sphere, and then from the 3-sphere to the 5-sphere, and then from the 5-sphere to the 7-sphere. And the scales at which these jumps happen are at scales 2 pi by 3, 4 pi by 5, etc. Scale 2 pi by 3, you now have this simplex supported on 3 points whose diameter is 2/3 of the way, 1/3 of the way around the circle. And then at scale 4 pi by 5, when this next transition happens from the 3-sphere to the 5-sphere, you have simplices, these 4-dimensional simplices supported on 5 evenly spaced points, whose diameter is 2/5 of the way around the circle. So I want to give you some intuition for why this transition from the circle to the 3-sphere happens. Um, Great. And this is the statement of the theorem. So the Rips complex of the circle is an odd sphere when you're in these critical regimes. 2 pi k over 2k plus 1, that traces out the numbers 0, 2 pi by 3, 4 pi by 5, 6 pi by 7, etc. Okay, so why do we jump from the circle to the 3-sphere? So I like to explain this as follows. Let's start with just a finite number of points and on the circle and look at the Rips complex of just a finite number of points. So what if I take the Rips complex of 6 evenly spaced points on the circle? And I'm going to be looking at scale 2 pi by 3. Okay. And so at scale 0, I just have the 6 points. At scale 2 pi by 6, I just have this circle. And then at scale 2 pi by 3, I have the clique complex of this set of edges. So perhaps you see an octahedron sitting there. In some sense, I have a equilateral triangle that forms the front face and the equilateral triangle that forms the back face. So the way I think about this is that I have 6 triangles that are the 6 rotations of this triangle, and together those form a cylinder. But in addition, I also have the 2 equilateral triangles, which are this front face and this back face. And those 2 equilateral triangles, they glue on disks to give me a 2-sphere. Okay, so this is a 2-sphere. Up to homeomorphism. Do you see that octahedron sitting there? The boundary of the octahedron? Okay, now let's go to 9 points. So I'm going to start at 9 points. And I'm going to look at scale 2 pi by 3. All right. So at scale 2 pi divided by 9, I just have all the edges. This picture is not going to be very good. Let me cheat. Okay. This is a little bit better. So what I have here is all of these edges. And I have 2 types of maximal simplex. So one type of maximal simplex is this blue tetrahedron, and I have all 9 rotations of that blue tetrahedron. So that forms a blue solid 3D torus sitting here. The other type of maximal simplex that I have is this red equilateral triangle and its 3 rotations. And so those glue on 3 disks, one for each equilateral triangle. So I have a disk up above, a disk down below, and a disk in the middle. And so that forms 2 copies of the 2-sphere, 2-sphere wedge, 2-sphere up to homotopy. So now what happens when I build the Rips complex on the entire circle is that I have not only all of this, infinite dimensional simplices, simplices of arbitrarily high dimension that I started with around the outside of the circle. And then I have not only one equilateral triangle that glues on, say, right here, but I have an entire circle's worth of equilateral triangles. So as I rotate this equilateral triangle around, I get a circle's worth of disks that I've glued on. So I think of this infinite dimensional solid torus that I started with as just a up to homotopy. It's a 3D solid torus sitting in Euclidean space in front of us. And then I think of the circle's worth of equilateral triangles that glues on as a circle's worth of disks that get attached. Okay. And so I pass through the point at infinity, I wrap back it around, and just like these equilateral triangles rotate back to each other, so do these disks wrap back to each other. So I've thought of this Rips complex up to homotopy as all of 3D plus the point at infinity, or in other words, this three sphere. Okay. Another way to think of this is as the three sphere is just the join of a circle with itself. So one circle would be the circle inside this solid torus, and this other circle would be this vertical circle here. And when I join two circles, I get the three sphere. So that is just some intuition for the jump from the circle to the three sphere. You probably saw this octahedron relatively explicitly, and then maybe you saw this wedge of two spheres. And then as I add more and more equilateral triangles, well, I really have this circle's worth of equilateral triangles. Questions about that? Okay. And then to a three sphere, if you glue on a circle's worth of four simplices, you get a five sphere. And to a five sphere, when you glue on a circle's worth of six simplices, you get a seven sphere. So these are all just joins. Um, the three sphere was the join of the circle with the circle's worth of critical triangles that appeared. And the five sphere was the three sphere that I had before, joined with the circle's worth of critical four simplices that appeared, etc. All right, so that's nearly the end of what we know. Let me tell you how much we don't know. So let's look at n spheres. We know by Hausmann's theorem that when you build the Rips complex on the n sphere, you recover the n sphere for small scales. We know that once you pass scale pi, you are contractible. And in the intermediate range, we know essentially nothing. With a slightly different topology, we know the first new homotopy type that appears. It's again the space we started with, the n sphere, joined with a parameter space, SON plus 1 mod AN plus 2 of critical simplices. So here the critical simplices are regular n plus 1 dimensional simplices that fill the n sphere. And then, in the two sphere, how many tetrahedra, regular tetrahedra appear to fill the two sphere? Well, I have all rotations of that tetrahedron, SO3's worth of rotations in 3D space, quotiented out by the rotational symmetries of the tetrahedron, the alternating group on four vertices. Um, but we know nearly nothing about the homotopy types here in this intermediate range. And this is a hard but inspiring question for me. Um, we do know that the homotopy type changes infinitely many times. Um, we've proved this by getting bounds on the homotopy connectivity of these complexes. So the homotopy connectivity in this range is always finite, but it's increasing towards infinity. So you have an accountably infinite number of different homotopy connectivities, therefore accountably infinite number of different homotopy types. So you conjecture that the homotopy type changes only countably many times, right? That's what happened for the circle. We had only a countable number of different homotopy types, even though there's an uncountable number of reals. So you could conjecture only countably many changes of homotopy type. That's unknown. You would conjecture that the homotopy connectivity is never decreasing. That's unknown. Even though these spaces are infinite dimensional, you would conjecture that they're homotopy equivalent to a finite dimensional CW complex, and that's unknown. So let me end just with some open questions. I talked about Rips complexes of spheres, but you could also look at Rips complexes of these other homogeneous manifolds. Not much has been known. Not much is known. Uh, Rips complex of the ellipse is quite interesting. So now it's not a Riemannian manifold, right? I have the restriction of the Euclidean metric. With the ellipse, we break symmetry. So instead of having a circle's worth of equilateral triangles appear at once, these two solid equilateral triangles appear first. And that's a lot like the octahedron example, where I have a circle up to homotopy, and then I glue on just two disks to get the two sphere next. And then only once all equilateral triangles appear do you then get the three sphere. So this might make you think of Morse theory or Morse spot theory. So when the ellipse, we had isolated critical equilateral triangles. But for the circle, you don't have isolated critical equilateral triangles, so you'd want a Morse spot theory. So there are a couple different candidate Morse theories, but none of them can recover the known examples already of the circle. So we need stronger Morse theories that work for these infinite dimensional settings. Um, okay. And let me end there. So thanks so much for your time and attention.
Thank you for the nice presentation. Let me stop the recording first. Second. Record. Stop recording.